Welcome back to Chapter 3 of Principles of Mathematical Analysis. In this section, we develop a single algebraic identity called summation by parts, and then watch it do a great deal of work. The identity is the discrete cousin of integration by parts, where integration by parts trades a hard integral for an easier one. Summation by parts trades a hard sum for an easier one. The payoff is a family of convergence tests for series of the form sum of a sub n times b sub n, where the factor b sub n is monotonic. From this one tool, we will get Dirichlet's test, the alternating series test that Leibniz knew, and a result about power series on the boundary of their disk of convergence. Let's begin. Here's the plan. We start with motivation, drawing the analogy with integration by parts and explaining why we care about sums of products. Then, we state and prove the partial summation formula itself, Theorem 3.41. With that tool in hand, we prove three applications: Dirichlet's test in Theorem 3.42, the alternating series test in Theorem 3.43, and a boundary convergence result for power series in Theorem 3.44. Finally, we summarize the key ideas. Let's set the stage. Many important series are not just sums of single terms, but sums of products. A term a sub n multiplied by another term sub en. The root test and the ratio test from the previous section are powerful, but they are really designed for absolute convergence. They say nothing useful when the terms change sign, or when convergence is delicate. We need a different tool tailored to products. Next, let's recall where such products come from. Here's the key idea, and the formula on the slide captures it. Integration by parts takes the integral of u with respect to v and rewrites it as the boundary term u times v minus the integral of v with respect to u. In effect, it moves the derivative off one factor and onto the other, turning a hard integral into an easier one at the cost of a single boundary term. Summation by parts is the exact discrete analog. Sums play the role of integrals, and forming partial sums plays the role of anti-differentiation. The practical upshot is that we get to integrate the oscillating factor, replacing it by its bounded partial sums, while we differentiate the tame factor by taking differences. Next, let's see what we gain. And here is the payoff. When one of the two factors, say b sub n, is monotonic and tends to 0, summation by parts converts the series into a form we can control, even though it may not converge absolutely. This single identity will give us three classical results: Dirichlet's test, the alternating series test known to Leibniz, and a theorem about convergence of power series on the boundary circle. Let's now build the tool itself. Here's the theorem. We are given two sequences, a sub n and b sub n. We form the partial sums of the first sequence. Capital A sub n is the sum of the a terms from index 0 up to n. By convention, we set capital A sub -1 equal to 0, which just makes the bookkeeping clean. The conclusion, equation 20, rewrites the sum of the products a sub n times b sub n between any two indices p and q. On the right, we no longer multiply a by b. Instead, we multiply the partial sums capital A sub n by the consecutive differences b sub n minus b sub n plus 1 plus 2 boundary terms. Compare this with integration by parts. Capital A plays the role of an antiderivative of a, and the differences of b play the role of the derivative of b. Let's prove it. The proof is short and purely algebraic. The first step is the central observation. Each term a sub n is the difference of two consecutive partial sums, capital A sub n minus capital A sub n minus 1. This is the discrete analog of recovering a function from its antiderivative. Substituting this into our sum, we replace every a sub n by that difference. Next, we split the sum into two pieces and reindex. In step 2, we split the sum into two separate sums, one with capital A sub en times b sub n, and one with capital A sub n minus 1 times b sub n. The second sum still refers to capital A at the shifted index n minus 1. So we reindex it by letting m equal n minus 1. This slides the range down by 1 and turns it into a sum of capital A sub n times b sub n plus 1. Now both sums involve capital A sub n, and we can compare them term by term. Now we line up the two sums. On the overlapping range, from p up to q minus 1, each capital A sub n appears in both sums, so we combine them to get capital A sub n times the difference b sub n minus b sub n plus 1. Two terms are left over. The first sum contributes its top term, capital A sub q times b sub q. The second sum contributes its bottom term, capital A sub p minus 1 times b sub p, with a minus sign. Putting these together gives exactly equation 20, the boxed identity on the slide. The proof is complete. Before we use it, let's appreciate why this identity is the right tool. Formula 20 is called the partial summation formula, or Abel summation, after the mathematician Niels Abel. Its great virtue shows up when the sequence b sub n is monotonic, that is, steadily increasing or steadily decreasing. In that case, every difference b sub n minus b sub n plus 1 has the same sign, so the sum on the right collapses into something we can bound cleanly. That is exactly the structure the next three theorems exploit. Let's see the first application. Here is our first and most important application, often called Dirichlet's test. Notice the hypotheses. We do not require that the series sum of a sub n converges. We only require that its partial sums capital A sub n stay bounded. The second sequence, b sub n, must be monotone decreasing and must tend to 0. Under just these conditions, the series of products converges. This is striking, because neither factor alone need give a convergent series. A classic example is the sum of sine of n times theta. Divided by n, the partial sums of the sines are bounded, and 1 over n decreases to 0. Let's picture those two hypotheses. This picture shows what the two hypotheses look like. On the left, the blue dots are the magnitudes of the partial sums, the absolute value of capital A sub n. Because a magnitude is never negative, the dots all sit above the axis, and the hypothesis says they never rise above the dashed red line at height capital M. That is exactly what bounded means here. The sizes stay capped by capital M, no matter how far to the right we go. Keep in mind that the partial sums themselves may even be complex numbers, which is why we track their absolute value rather than the sums directly. On the right, the amber dots are the values b sub n. They march steadily downward toward the axis, never increasing, approaching 0. The whole proof lives in the tension between these two pictures. One factor is held in check by boundedness, the other is squeezed down to nothing. let's see the strategy that combines them. Before the formal estimate, here is the plan. The tool is the partial summation formula we just proved. The goal is to show the series satisfies the Cauchy criterion. The tail sum from index P to index Q can be made as small as we like once P is large enough. The key fact that makes this work is the combination of two hypotheses. Boundedness of the partial sums, capital A sub n, lets us pull out a constant, and monotonicity of B sub n lets the differences telescope. Together they collapse the whole estimate down to a constant times B sub P, which tends to 0. Let's carry it out. Step 1. Since the partial sums are bounded, choose a constant capital M, with the absolute value of capital A sub n at most capital M for every n. Now apply formula 20 to the tail sum and take absolute values. Every capital A appearing is bounded by capital M, so we factor capital M out. Here is the crucial point, which I want you to watch on the slide. Because B sub n is decreasing, each difference B sub n minus B sub n plus 1 is non-negative. That is what lets us pull the absolute value inside and replace each term by its size without sign cancellation working against us. Next, we evaluate that bracket. Step 2 finishes the argument. The sum of the consecutive differences telescopes. Almost everything cancels, leaving just B sub P minus B sub. Adding the two leftover boundary terms, B sub Q and B sub P, the B sub Q pieces cancel, and we are left with twice capital M times B sub P. This is the collapse we predicted. Now we use that B sub n tends to 0. Given any positive epsilon, choose an index capital N, so that B sub capital N is at most epsilon over twice capital M. Then, for every P beyond capital N, the tail sum is at most epsilon. That is precisely the Cauchy criterion, so the series converges. Let's apply this to alternating series. Now a famous special case. Condition A says the absolute values of the terms are decreasing. Condition B says the signs alternate. The odd terms are non-negative. The even terms are non-positive. So the pattern of signs is plus, minus, and so on. Condition C says the terms tend to 0. Whenever these hold, the series converges. As the remark notes, series with this alternating sign pattern are called alternating series, and this convergence result was already known to Leibniz. The standard example is 1 minus 1 half plus 1 third minus 1 fourth, and so on. The alternating harmonic series. First, let's build some intuition for why it converges. Here is the geometry behind the alternating series test. Because the terms add and subtract in turn, each partial sum lands on the opposite side of the previous one. On the slide, S sub 1 sits far to the right. Then S sub 2 jumps to the left. S sub 3 jumps back to the right, but not as far. And so on. Since the terms shrink in size, every jump is shorter than the one before, shown by the arcs getting smaller. The odd-numbered partial sums come down from the right, while the even-numbered ones climb from the left, and they close in on each other like a tightening bracket. The single point they trap, marked S in red, is the sum of the series. This nesting is exactly why convergence is forced. Now let's see how Dirichlet's test makes it rigorous in a single line. The proof is a one-line application of Dirichlet's test, and it shows the power of having the general tool. We factor each term C sub En into a sign part and a size part. let a sub en be minus 1 to the n plus 1, which is plus 1, minus 1, plus 1, and so on, and let b sub n be the absolute value of c sub n. Then a sub n times b sub n reproduces c sub n, signs and all. Now check the three hypotheses of theorem 3.42. The partial sums of the alternating plus and minus ones are always either 0 or 1, hence bounded. The sizes b sub n are decreasing by assumption a, and they tend to 0 by assumption sot c. All three conditions hold, so Dirichlet's test gives convergence at once. Let's turn to power series. Our last application reaches into the complex plane. Recall from the previous section that a power series with radius of convergence, one converges inside the unit disk and diverges outside it. The behavior right on the boundary circle, where the absolute value of z equals 1, is usually subtle and was left open. This theorem settles it under extra hypotheses. If the real coefficients c sub n decrease to 0, then the series converges at every point on the boundary circle, with the single possible exception of the point z equals 1. The point z equals 1 really can fail. Think of the coefficients 1 over n, which give the harmonic series there. Let's picture what this says. This picture summarizes the theorem in the complex plane. The shaded blue disk is the interior, where the absolute value of z is less than 1. There the power series converges, as we already knew from the previous section. Outside the disk, it diverges. The new content is the thick green boundary circle, where the absolute value of z equals 1. The theorem says the series converges all the way around that circle, with one exception, the point z equals 1, drawn as the open red dot on the right. There, the series may fail, and the proof will show exactly why this single point is special. Let's prove it. Once more, Dirichlet's test does the work. We take a sub n to be z to the n, and b sub n to be the coefficient c sub n. The partial sums capital A sub n are then partial sums of a geometric series, which we can evaluate in closed form, 1 minus z to the n plus 1, all over 1 minus a z. When the absolute value of z is 1, the numerator has absolute value at most 2, so the whole expression is bounded by 2 over the absolute value of 1 minus z. This is a fixed bound, independent of n, as long as z is not equal to 1. So the partial sums are bounded. The coefficients c sub n decrease to 0 by hypothesis. Both conditions of Dirichlet's test hold, and convergence follows. Notice exactly where z equals 1 is excluded. There the denominator, 1 minus z, vanishes, and our bound blows up. Let's summarize. Let's review what we covered. The foundation of the whole section is the partial summation formula, theorem 3.41. It is the discrete version of integration by parts. It rewrites a sum of products a sub n times b sub n in terms of the partial sums, capital A sub n, and the differences of b. This one identity powered everything that followed. Next, the main application. The central application is Dirichlet's test, theorem 3.42. It says that if the partial sums of a sub n stay bounded, and the second factor, b sub n, decreases monotonically to 0, then the series of products converges, even when it does not converge absolutely. This is a genuinely new kind of convergence test, complementing the root and ratio tests. Next, its two consequences. From Dirichlet's test, we obtained the alternating series test, theorem 343, known already to Leibniz. If the terms alternate in sign and their absolute values decrease to 0, the series converges. We proved it in a single line by factoring out the alternating sign and applying Dirichlet. Next, the complex variable consequence. Finally, Theorem 344. Apply the same idea on the boundary of a power series disk. If the coefficients decrease to 0, the series converges everywhere on the unit circle except possibly at z equals 1, where the geometric partial sums are no longer bounded. The lesson of the whole section is that one clever algebraic identity, summation by parts, unlocks a whole family of delicate convergence results. In the next section, we turn to absolute convergence and study how it differs from the conditional convergence we have been exploiting here. See you there.